Okay, so in these types of problems, you're saying that the change in potential energy turns into kinetic energy, right? So Q times change in VE is equal to 1/2 mv squared, right? The work turns into kinetic, right? And our mass for an electron is, in the data packets, a 9.11 times 10 to the minus 31st kilograms. The charge is really a negative 1.602 times 10 to the minus 19th coulomb. So really this should be a negative change in voltage. Nobody does that, I'm just saying. Okay, so let's just plug in here. Notice that this speed here is significantly less than the speed of light, right? 3.8 times 10 to the 5th is much less than 3.0 times 10 to the 8th. Okay, so we don't have to really worry about any relativity effects. When you start getting half the speed of light, you better be careful. Okay, so let's just plug into our, we got 1.602 times 10 to the minus 19th. Our change in potential is what we're trying to find. And then that is 1/2 the mass of an electron times 10 to the minus 31st, right? Times 3.8 times 10 to the 5th squared. So now we're solving for that. So I'm going to go 0.5 times 9.11 E minus 31 times 3.8 E5 squared. By the way, you don't need parentheses around that. The TI engineers did that one correctly. Let's see, 1.602 E minus 19. And I'm getting that the change in electrical potential is a whopping 0.41057 volts, or about 0.411 volts. Okay. Now, really, actually, for an electron, you'd need to accelerate it. You would want to accelerate it through, because this would have to be negative. This guy's negative. This would have to be a negative potential. Okay. So we would accelerate it through some negative potential to do that. Why is that? Let's make a positive. Here's negative, right? The electron is going to accelerate this way, right? So it's going to accelerate toward the positive, okay?